According to National Electrical Code Article 310.15b16, parallel conductors for services must have the same material, size, and insulation type. The use of copper for the service conductors and aluminum for the secondary conductors is a violation of this code. The ampacity of the paralleled aluminum conductors is not the same as the ampacity of the copper service conductors. This can lead to voltage drop issues and potential overloading of the secondary conductors. Aluminum and copper have different electrochemical properties, and when connected together, they can create a galvanic cell that leads to corrosion and safety hazards. The electric cooperative has a contractual obligation to provide a secondary service that meets the specifications of the electrical contractor. If the secondary conductors do not meet these specifications, the electric cooperative could be held liable for any damages. If the electric cooperative refuses to correct the issue, the electrical contractor could consider legal action to enforce the contractual obligations or seek compensation for any additional costs incurred due to the improper secondary conductors. The electrical contractor can also report the issue to the local building authority or the state electrical board. Regulatory agencies have the authority to inspect electrical installations and enforce code compliance. Firstly, take photos and gather any relevant documentation related to the improper secondary conductors. Secondly, contact the electric cooperative in writing, clearly stating the code violations and requesting that they correct the issue. Thirdly, if the electric cooperative is unwilling to cooperate, consider consulting with an attorney to explore legal options. The electrical contractor should ensure that all electrical work on their end complies with the NEC and any local codes. It is important to note that the electric cooperative has the right to choose the materials and methods used for their secondary distribution system. However, they must comply with code requirements and provide a safe and reliable service that meets the needs of their customers. When dealing with an 800 amp single-phase 240 volt alternating current service, specifically one split into two 400 amp services, several critical considerations regarding conductor sizing and material come into play. The initial observation that the electric cooperative installed parallel 350 kc aluminum conductors for the 240 volt lines and 4/0 aluminum for the neutrals, while the electrical contractor used 500 kc copper wires from the meters to the breaker panels, raises significant concerns about code compliance and safety. Article 310.15b16 of the National Electrical Code addresses the requirements for parallel conductors, stating that they must be of the same material, size, and insulation type. The discrepancy between the aluminum secondary conductors provided by the cooperative and the copper service conductors installed by the contractor immediately violates this provision. The rationale behind this rule is to ensure that the conductors share the load equally and that there are no imbalances that could lead to overheating or failure. Using dissimilar metals can also cause galvanic corrosion, further compromising the integrity of the electrical system. Beyond the material mismatch, it's crucial to evaluate the ampacity of the aluminum conductors compared to the copper conductors. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. For an 800 amp service, the conductors must be sized to handle this current safely. Copper has a higher ampacity than aluminum for a given conductor size. Therefore, simply assuming that the aluminum conductors are adequate based on the 800 amp service requirement is insufficient. A detailed ampacity calculation is necessary considering the ambient temperature, the number of conductors in a raceway, and any applicable diluting factors. For example, at 75 degrees Celsius, a 500 kc copper conductor typically has a higher ampacity than a 350 kc aluminum conductor. If the aluminum conductors cannot carry the required current, they will overheat, potentially causing insulation damage, fire hazards, and premature failure of the electrical system. Furthermore, voltage drop must be considered. Voltage drop is the decrease in voltage along the length of a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of electrical devices, and even damage sensitive electronic equipment. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders and services. Aluminum conductors have a higher resistance than copper conductors of the same size, leading to greater voltage drop. The electric cooperative's choice of 350 kc mil aluminum conductors may result in an acceptable voltage drop, especially under heavy load conditions. To calculate voltage drop, one needs to know the conductor length, the current flowing through the conductor, and the conductor's resistance per unit length. The formula for voltage drop is voltage drop equals current times resistance. By comparing the calculated voltage drop to the NEC recommended limits, one can determine whether the aluminum conductors are adequately sized for the application. The connection between aluminum and copper conductors introduces another set of concerns. Aluminum and copper are dissimilar metals, and when they come into contact in the presence of moisture, they can create a galvanic cell. This electrochemical reaction causes the aluminum to corrode, which increases its resistance and further reduces its ability to carry current. Over time, the corrosion can weaken the connection, leading to loose connections, arcing, and potential fire hazards. To mitigate these risks, special connectors and joint compounds are required when connecting aluminum and copper conductors. These connectors are typically made of bimetallic materials that minimize galvanic corrosion, and the joint compounds help to prevent moisture from entering the connection. It is crucial to ensure that these connectors are properly installed and maintained to prevent long-term reliability issues. Given these concerns, it is essential to take appropriate actions to address the situation. The electrical contractor should begin by documenting the issue thoroughly. This includes taking photographs of the conductor installation, noting the conductor sizes and materials, and recording any relevant measurements such as voltage and current readings. The documentation should be comprehensive and accurate, as it may be needed as evidence in future discussions or legal proceedings. The next step is to communicate with the electric cooperative in writing. The communication should clearly outline the code violations, the potential safety hazards, and the expected corrective actions. It should also reference the specific sections of the NEC that are being violated and explain the rationale behind the code requirements. This formal communication serves as a record of the contractor's concerns and provides the cooperative with an opportunity to address the issue. If the electric cooperative is unresponsive or unwilling to cooperate, the electrical contractor may need to escalate the matter to regulatory agencies. Local building authorities and state electrical boards have the authority to inspect electrical installations and enforce code compliance. By filing a complaint with these agencies, the contractor can request an inspection of the service and a determination of whether the installation meets code requirements. If the regulatory agency finds that the installation is not in compliance with the code, they can issue a notice of violation and require the electric cooperative to make the necessary corrections. In some cases, legal action may be necessary to resolve the issue. If the electric cooperative has a contractual obligation to provide a service that meets certain specifications and they have failed to do so, the electrical contractor may have grounds for a breach of contract claim. Similarly, if the improper installation has caused damages such as equipment malfunction or property damage, the contractor may have grounds for a negligence claim. Consulting with an attorney can help the contractor understand their legal options and determine the best course of action. Throughout this process, the electrical contractor must ensure that all electrical work on their end complies with the NEC and any local codes. This includes properly sizing and installing the copper conductors from the meters to the breaker panels, using appropriate connectors for any aluminum to copper connections, and verifying that the electrical system is properly grounded and protected. By adhering to code requirements, the contractor can minimize their liability and ensure the safety of the electrical installation. While the electric cooperative has the right to choose the materials and methods used for their secondary distribution system, they must comply with code requirements and provide a safe and reliable service that meets the needs of their customers. In this case, the cooperative's choice of aluminum conductors appears to be inconsistent with the NEC and may pose safety hazards. By documenting the issue, communicating with the cooperative, and involving regulatory agencies if necessary, the electrical contractor can take steps to ensure that the service is brought into compliance with the code and that the safety of the electrical installation is protected. A deep dive into the electrical engineering principles further clarifies the importance of these considerations. Electrical conductivity, represented by the symbol sigma, is a measure of a material's ability to conduct electric current. Copper has a higher electrical conductivity than aluminum, meaning that for a given size, copper can carry more current with less resistance. The resistivity, represented by the symbol ρ, is the inverse of conductivity and indicates how strongly a material opposes the flow of electric current. Aluminum has a higher resistivity than copper, which is why larger aluminum conductors are needed to carry the same amount of current as smaller copper conductors. The ampacity of a conductor is determined by its ability to dissipate heat. When current flows through a conductor, it generates heat due to the conductor's resistance. The amount of heat generated is proportional to the square of the current and the resistance of the conductor, as described by Joule's law, which states that power equals current squared times resistance. If the heat generated exceeds the conductor's ability to dissipate it, the temperature of the conductor will rise, potentially damaging the insulation and leading to failure. The NEC provides ampacity tables that specify the maximum allowable current for different conductor sizes and types, taking into account factors such as ambient temperature, the number of conductors in a raceway, and the type of insulation. These tables are based on extensive testing and engineering analysis to ensure that the conductors can operate safely without overheating. Voltage drop is another critical consideration in electrical system design. As current flows through a conductor, the voltage decreases due to the conductor's impedance. The amount of voltage drop is proportional to the current, the conductor length, and the conductor's impedance, as described by Ohm's law, which states that voltage equals current times resistance. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of electrical devices, and even damage sensitive electronic equipment. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders and services. To calculate voltage drop, one needs to know the conductor length, the current flowing through the conductor, and the conductor's resistance per unit length. The formula for voltage drop is voltage drop equals current times resistance. By comparing the calculated voltage drop to the NEC recommended limits, one can determine whether the conductors are adequately sized for the application. The connection between aluminum and copper conductors introduces additional challenges due to the dissimilar metals' electrochemical properties. When aluminum and copper come into contact in the presence of moisture, they form a galvanic cell. This electrochemical reaction causes the aluminum to corrode, which increases its resistance and weakens the connection. Over time, the corrosion can lead to loose connections, arcing, and potential fire hazards. To mitigate these risks, special connectors and joint compounds are required when connecting aluminum and copper conductors. These connectors are typically made of bimetallic materials that minimize galvanic corrosion, and the joint compounds help to prevent moisture from entering the connection. It is crucial to ensure that these connectors are properly installed and maintained to prevent long-term reliability issues. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and energize the circuit. Bonding ensures that all metal parts of the electrical system are electrically connected, preventing voltage differences that could create shock hazards. The NEC specifies detailed requirements for grounding and bonding, including the size and type of grounding conductors, the methods for connecting grounding electrodes, and the requirements for bonding metal enclosures and equipment. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing damage to the wiring and equipment. The NEC specifies the types and sizes of overcurrent protection devices that are required for different types of circuits, taking into account the conductor ampacity, the type of load being served, and the potential for overloads and short circuits. In summary, the choice of conductor materials and sizes for an 800 amp single-phase 240 volt alternating current service requires careful consideration of electrical conductivity, ampacity, voltage drop, galvanic corrosion, grounding, bonding, and overcurrent protection. Compliance with the NEC and other applicable codes is essential to ensure the safety and reliability of the electrical installation.